All right, so we talk about abstract concepts like confusion and diffusion. Now let's see some practical examples and how we design block ciphers. So currently there are three major categories in block cipher design: substitution permutation networks, Feistel networks, sponge functions, permutation-based functions. These are more recent ones, more popular ones. So you can think about like this. DES, one of the oldest standards, is a Feistel network. AES, current standard, is substitution permutation network. And ASCON, new lightweight standard of NIST, is a sponge function or a permutation-based design. There's also ARCS design, actually addition, rotation, XOR, but actually that design only uses addition, XOR, and rotation, but can be fit in one of these categories somehow. So this is why I didn't explain it as a third case, but you can also think about it as a third design algorithm. So designing something big makes it harder to analyze. So what we do is as follows: just design a round which includes confusion and diffusion, then repeat it R many times. That is the main idea behind block ciphers. Key schedule is another part of the design. So you have the secret key, but instead of using the key directly in every round, a key schedule algorithm is used to generate round keys from the secret key. So this way you kind of cause more diffusion and confusion actually. So let's first look at the substitution permutation networks. Generally, one round of substitution permutation network consists of 3 layers: key addition, which combines the round key with the plaintext or the input. Substitution layer provides confusion. Here we can use S-boxes, which is a nonlinear operation. In order to create confusion, we need the nonlinear operation. So S-boxes are one of the favorite examples. But for this reason, people always think that you have to use S-boxes, but you don't have to. There are block ciphers which doesn't have any S-box. You can use like modular addition and so on to provide nonlinearity. Permutation provides diffusion. You can, change the places of bits, multiply with the matrix, and so on and so forth. Any operation that causes diffusion would be fine. So AES and present are examples of SPN. And after these designs, I will briefly explain how present works. Okay? Because in the future, we will try to break some rounds of present using differential cryptanalysis. So this is why we are focusing on present. All right, let's look at the general picture of a substitution permutation network. You have the plaintext block here. You have your secret key, and you fed it into key schedule algorithm, which provides round keys. In some lightweight designs, you don't have key schedule. You simply use the key in every round. So, have faster algorithms. But this is most of the time not suggested, which you will see that makes sense in, related key attacks and so on. Anyway, you take your round key and add it to plaintext. Generally, we XOR, but you don't have to, right? You can also do some other operations, but somehow you combine the input with the round key. Then you have layers like substitution and permutation, okay? Add round key. So you repeat this process. You have to start with round key and finish with round key, because for instance, if I don't put addition of round key here, what I can do is as follows. I captured the ciphertext. So there's a permutation here. So I can take the inverse of this permutation, also take the inverse of the substitution layer and reach here. So this way, these 2 layers wouldn't provide any security at all, right? I want to hide my internal steps by using an operation which includes secret information, so that when somebody captures the plaintext block, they cannot go from here to here or any other intermediate parts, okay? So this is actually how the security is obtained. So this is why we will use differential cryptanalysis here, so that when I change a bit here, I will obtain another plaintext block here. I will also encrypt it and obtain a ciphertext here. But the thing is that I know this plaintext, so I only change a single bit. So after you edit the round key, I don't know what will be the output here or here, but I still know that their XOR is still the change of that single bit. So I can, follow the changes I made in the intermediate rounds. Although I don't know their values, I can see what kind of changes I made. This is what we will be dealing with in the following week when we talk about statistical attacks and then differential cryptanalysis as an example. So here's the basic example. I will give it in more detail in the next slide. So I will briefly explain it here. So here is the one round of present block cipher, which is ISO standard for lightweight cryptography. So it has a 64-bit block size. So each line here represents a single bit. Key addition is the XOR of the input and the round key, which is also 64-bit. You simply XOR bit by bit. Although your master keys can be 80 bits or 128 bits, key schedule provides 64-bit round keys. This is why you can simply XOR these two values. Then you have an S-box, actually 16 S-box, but all of them are identical, which takes 4-bit input and provide 4-bit output. So assume that your 4-bit input is all 0. In the hexadecimal notation, it is this. And this S-box replaces it with C. This is actually the place you create confusion. Okay, and C in hexadecimal is, if you convert into integer, it is 12. In the binary notation, if the rightmost bit is the least significant bit, then it turns into 1, 1, 0, 0. Right? This is your confusion layer. In the diffusion layer, you switch the places of the bits. So you repeat it 31 times. So take this picture, put it 31 times there. At the final part, add in another round key, and this is your present. Okay. Very nice design, specifically for hardware. I haven't explained key schedule and so on, but again, I have slides in the following part where I will explain in a lot more detail. So let's talk about Feistel networks, introduced by Horst Feistel. A round of a Feistel network consists of a round function and a swap operation. ID is as follows. I will also show a picture, but the B-bit input is divided into 2 halves. Round function is applied to one half, and the output is XOR to the other half. Key material is used inside the round function most of the time. Then the place of these halves are swapped. So let me make it more clear with the picture. Again, the key is fed in the key schedule, and you have your round keys. So now you divided the plain text as the right and the left part. Okay, right part goes unaffected and becomes the left part in the next round. But right part is also fed into a round function. Here you have actually confusion and diffusion layers, also key addition layers. And the output is XORed with the left part. Now the left part is modified, and it becomes the right part in the next round. So it has some advantages, because when you're decrypting backwards, for instance, if we go back, when we are decrypting here, for instance, you have the ciphertext and the secret key, you have to perform the inverses of all of these operations to obtain plain text. So this means that you have to implement inverse of all of these layers. Because in the encryption part, you go from here to here. In the decryption part, you have to go other way against these arrows. Okay? So in the hardware, you have to implement the inverses, so it will take more place and so on. But in the Feistel network, this is not necessary. Because they look at it in this way. In the encryption part, you have the round function, and you fed the input from here, right? And do the encryption and so on. When you want to decrypt, you have the right and left part of the ciphertext. So instead of going from here to here, actually what you do is as follows. Take the right part, fed it into the round function, XOR it is here. So this way you obtain the value here. So you still perform the round function in the same order. But instead of performing this one, you perform this one. Actually, only thing that changes the order of the round keys. In the encryption, you use this one first. In the decryption, you use the last. That's it. This is why this is very efficient and so on. So here's a generalized Feistel example. In my previous example, I had 2 lines, but CLEFIA is one of the other ISO standards developed by Sony, and it is used for digital rights management in many Sony applications. So this time, instead of 2 lines, they have 4 lines, because this time the block size is 128 bits. So each line here actually represents 32 bits. So, you know, it is like 2 Feistel networks combined together. This is still unbroken and very nice algorithm. Okay. So instead of AES, you can use this, for instance, in lightweight applications. In F0 and F1, you have just 8x8 S-box like AES, matrix multiplication, and so on. Very similar to AES design, but it is not SPN, it is Feistel, unlike AES. So let's talk about pros and cons. I briefly explained a few of them, but let's look at the pros of the Feistel. Encryption algorithm is identical to the decryption algorithm. Only the order of the round keys change. But the good thing with the SPN is that a single round affects the whole input because you fed it into substitution and confusion layer. But inverse of these sentences can be provided as the cons. In the Feistel, a single round only affects half of the input. In the SPN, the decryption procedure requires the inverse of the substitution and permutation layers, which is, bad thing when you implement. In the software, this is not a problem, but in the hardware, it might be a problem. So finally, let's move on to third design, which is becoming more popular and popular these days because the sponge constructions are a nice way of designing block ciphers or hash functions, depends on your design. This is the full picture of ASCON. Associated data is used when you have data that you want to provide authentication but not encryption. So in this picture, just assume that this part doesn't exist. Okay, let me briefly explain how we perform encryption. So you have a huge internal state, like in this case, 320 bits. You fill it initially with IV, secret key, and nonce. IV is fixed, key is your secret key, nonce is randomly chosen every time, and it should be different every time. Okay, so you have an internal state of 320 bits. You perform permutation here, but permutation contains confusion and diffusion layers like S-box operation and shifts and that kind of stuff, XORs. So you have an internal state. You make it complex by performing confusion and diffusion layers here. So now the output is something different. And you take 64 bits plain text block here, XOR it with the top 64 bits of the internal state, and provide the result as the ciphertext of the 64 bits. Then you made operation on the internal state again, then take the second block and so on. This way you provide ciphertext. And good thing is that you perform a little more operation and provide the tag here. This is authentication tag. So this is authenticated encryption algorithm. It doesn't only solve the problem of confidentiality, it also solves the problem of authentication because it provides both ciphertext encryption, but it also provides message authentication code, in other words, a tag. So if we have the time, I will also show you how to implement ASCON and how we can attack in smaller rounds of it and so on. So let's talk a little bit more about design considerations for different platforms. So ASCON is important, by the way. Just 2 months ago, it became NIST standard. This is important. They won the lightweight competition. Now they are the standard. Aside from AES, this is the only standard NIST have, because they also have triple disk, but they will stop supporting in 2024. Another standard is skipjack, but it provides 80 bits secret key. So NIST only allows it for legacy use. Okay, so this is important. Most probably in the future, you will see a lot of IoT design which directly supports ASCON. So this way they can have NIST approval, and this way, we can have more secure IoT devices in the future. So a lot of people doesn't know the name ASCON yet, but it will be more popular maybe in 5 years and so on. So hardware versus software. Hardware implementations can easily work on bits. Since most programming languages focus on bytes, bit operations are more costly on software. You probably observed it when you looked at present. If we go back to present picture, here we are swapping bit positions. Just think about it implementing it in C or Python. Right? In software, this is a problem. Cipher design also determines the number of gates required to perform encryption on hardware, which determines the area required. This is important for IoT devices because the smaller is cheaper. This is why you don't want to actually put any encryption algorithm, because you lose security, but it will be cheaper, right? This is why there isn't any standards for these IoT devices. So this is why we have many disasters happening. This is why actually lightweight crypto competition is nice. Maybe in the future, there will be some standards forcing IoT devices to include either AES or ASCON if they have enough computational power and so on. Code size or required memory is not a big problem for software implementations due to fast CPUs and large RAM, but for smaller devices, this is a problem. There are still devices that have less than 64 kilobytes. Think about Commodore 64. In 2023, you have devices which has less memory than Commodore 64 because they're really, really small. okay? Or you have 4-bit microcontrollers still. So code size or record memory is also important, which people generally don't care much. Speed versus security. Speed is generally measured as throughput. Adding more security measures, for instance, increasing the number of runs, increases security, right? Because you are adding more confusion and diffusion, but reduces the speed. So you are trying to find a sweet spot so that the algorithm is both secure and fast. And I also need to add something here. There are some attacks which work regardless of the number of runs. So if you design something bad, it doesn't matter how many runs it has. For instance, an invariant subspace attack works regardless of how many runs you have. Or if there are many basic symmetries in the design, you can do some kind of attacks that uses these symmetries. Ciphers performing well on hardware or software may not be suitable for constrained devices, for RFID systems or sensor networks due to limited memory, battery, or computational power. This is why we talk about lightweight cryptography. So we need lightweight cryptography. We have a completely another course about it. You can watch the videos if you're interested. So let me finish with this picture. So there are many ISO standards. These ciphers are standards and they are not patented. So you can go and implement it as you like. So triple dash, Mystic, Cas128, height, AES, Camel, Seed are the ISO standards for block ciphers. These three are lightweight standards, ISO standards. LEA edits, I think, in 2019. So these were there years ago, but LEA edit. This is the addition rotation XOR. So present is SPN. This is Feistel. So this is addition rotation XOR. If you go to NIST side, we had AES for a very long time. Skipjack had 80-bit key, so it is only allowed by legacies. And good thing is that it is designed by NSA. So if you want to see how NSA's mind works, it is a nice algorithm to check the design. We have triple dash. Although NIST said that they will support 112-bit security until 2030 and more, they say that they will not be supporting triple dash after 2024. But the strange thing is that many credit cards actually use this algorithm in contactless payments. So I don't know what will happen when you try to use them in the United States after 2024. So we will wait and see. But as you can see, now we have ASCON here since February 2023 because they won the NIST lightweight competition. So these two actually will be taught. Maybe 10 years later, I will still be teaching these algorithms. So they're really important. Of course, everybody heard AES, but ASCON is becoming famous due to this competition. They actually won another competition, Ciphers competition, years ago, but it was designed by academicians. So, but this time it is a NIST competition, so it will be American standard. This means that it will be an international standard soon.